In this Theoretical Thursday, AJ and I will be considering a classic physics experiment that not only demonstrates the wave nature of light, but also allows one to determine the wavelength of a beam of light. The experiment we will be conducting is called the Slit Experiment, first performed by physician and physicist Thomas Young in 1801. The experiment in simplest form consists of a beam of monochromatic light that passes through a small slit in a screen that passes through another screen with two slits, S1 and S2. After the light passes through the two slits, it shines on a distant screen where an interference pattern of bright and dark fringes is observed.
Laser. Two pencil heads. Shine laser through gap. Three pencil heads. Two slits. Shine laser through gap.
Ooh. Equation for Young's two-split experiment can be represented by the path difference, change in L, equals d times sine theta. As a result, the bright fringe closest to the midpoint occurs at the angle theta given by the condition d times sine theta equals lambda, or sine theta equals lambda over d. Okay. In general, a bright fringe occurs whenever the path difference, change in L, equals d times sine theta is equal to m times lambda, where m equals 0, plus or minus 1, plus or minus 2, and so on. Therefore, we find that bright fringes satisfy the following conditions. This equation represents conditions for bright fringes or constructive interference in a two-split experiment. D times sine theta equals m times lambda. Note that m equals 0. Note that the m equals 0 fringe occurs at theta equals 0, which corresponds to the central fringe. In addition, positive values of m indicate fringes above the central bright fringe. Negative values indicate fringes below the central bright fringe. Between the bright fringes, we find dark fringes where destructive interference occurs. The condition for a dark fringe is that the difference in path lengths be plus or minus lambda over 2, plus or minus 3 lambda over 2, plus or minus 5 lambda over 2, and so on. This equation represents conditions for dark fringes or destructive interference in a two-split experiment. Positive m integers are used in above central bright fringes, while negative m integers are for below central bright fringes.
Now we will do a problem. Two slits with a separation of 8.5 times 10 to the negative 5 meters create an interference pattern on a screen 2.3 meters away. If the 10th bright fringe above the central fringe in the linear distance of 12 centimeters above the central fringe, what is the wavelength of the light used in the experiment? To find the wavelength of light used in the experiment, we need to calculate the angle of the 10th bright fringe using the equation y is equal to L tangent theta. Now we are going to manipulate this equation so it looks like theta is equal to the inverse tangent of y over L. Now if we plug in the numbers here, the inverse tangent of 0.12 meters over 2.3 meters is going to equal an angle of 3 degrees. Now that we found the angle of the 10th bright fringe, we are going to use the equation sine theta is equal to m wavelength over d to find the wavelength. So if we manipulate this equation to find the wavelength, it will look like this. And then when we plug in the numbers, it's going to be 8.5 times 10 to the negative 5th meters over 10 times the sine of the 10th bright fringe, and that is equal to 4.4 times 10 to the negative 7, or 440 nanometers.
In conclusion, this experiment and problem proves that light does in fact travel in waves and not corpusculouses as Newton once referred to them.